Awesome, let's get started then. Hey everyone, I'm Vandana. I'm a product manager based in the US, and with me I have.
Hi, I'm Kritika. I'm a software engineer dialing in from Canada.
So, we both first met while working together a couple of years back, and then we stayed connected for our shared love for tech, learning, and geeking out over system design.
So today we thought, why not host a fun little watch party? No pressure, just two of us catching up on all of the stuff. Some solid concepts that power real world products.
Yeah, from foundational concepts to what's trending in engineering and architecture, and we are here to just learn, question, laugh, and occasionally we're gonna pause the video and say like, "Wait, what just happened?"
Exactly. So grab a snack, open your notebook, whatever works, and let's
Let's
start
start
watching.
watching. Okay.
Our deep dive series. Today we're going to be talking about Elasticsearch, which is one of the most popular and powerful open source distributed search engines. Reminder that our deep dive series is intended to give you depth that's going to be relevant for your interviews. And so what we're going to be trying to cover here are both how technologies can be used in an interview and in a system design setting, as well as how they work so that you can understand the internals and answer questions that may come up. I'm Stefan. I am one of the co-founders of Hello Interview. I've worked as a senior manager at both Meta and Amazon, and over the course of my career, conducted north of 2,000 interviews. Very familiar with how interviewers tend to think about the process and hoping to share some of those insights along the way. This session is going to be divided into two parts. In the first part, we're going to talk about how to use Elasticsearch. This is particularly relevant for interviews where search is actually not the primary functionality, or in certain types of interview, like the product design interview at Meta, or interviews for full stack engineers at startups, where your interviewer wants to see you solve problems, not necessarily you have deep knowledge of how distributed systems work. In the second half of the session, what we're going to do is peel back the layers of Elasticsearch and talk about some of the design decisions under the covers and how clusters function. The goal there is both to give you some insights into how it actually functions, but also some inspiration for your own designs, especially as they pertain to more infra-style interviews. Before we get too deep, just a reminder that all of this information is available on our website, hellointerview.com. There we collected a bunch of deep dives on technologies that we really think you should know, just like Elasticsearch, as well as common problems that you might encounter in a system design interview. In these instances, we've broken it down, walked through some of the different choices that you might need to make, and then given you an indication as to which ones are great and which ones are probably not the ones that you might want to use in an interview. We've also recently launched our Guided Practice product. Guided Practice is solving this problem.
I just feel like the, the first 30 seconds are just like promotional video for this guy's Hello
Yeah,
Interview.
and I'm getting concerned because he's being very open about interviews, right? Like I guess the other guy wasn't.
Problem.
Yeah.
Yeah, I think we should just skip the introductory
Yeah, we
part
can
and
skip.
hope. I'm
Yeah.
just like flying blind now. I'm because I don't know when he's gonna start this.
Right, yeah.
I'll just maybe just go to like 3:40, 3:30. Okay. Yeah, I will see if this is gonna work. Okay, it looks like it's two.
Probably not the ones that you might want to use in an interview. We've also recently launched our Guided Practice product. Guided Practice is solving this problem and allowing
I'm
people to
sorry
watch
about this.
videos to give the search some criteria. Let's pretend that I'm complement to this video. In the first half of this video, we're going to talk about how to use Elasticsearch in a system design setting. For that, we first need to talk about search. So what is search? Well, typical search experiences are comprised of a few different pieces. First, I'm going to give the search some criteria. Let's pretend that I'm searching for books. I'm actually going to use a bookstore as a motivating example throughout this video. So maybe I want to search my bookstore for books that have the title that contains great and for a price that's less than $13. That's potentially describing a lot of books. So I might want to sort those books in my search results. In that case, I might specify that I want to see the most recently published books that contain the word great. In my search result page, I might also have an option to break down the search and refine what I've described. These are typically called facets or faceted search. And one example is I might want to refine by the publisher, maybe Hachette or Simon & Schuster. Boo Hachette for suing the Internet Archive. Anyway, the net of a search experience.
Facets are basically filters, right?
Well, if yeah,
It's actually when I didn't know until I joined my work, like apparently the left hand nav of your any shopping page that you go, the left hand side, there's a bunch of
right.
filters that allows you to like say, hey, color equals red, size equals XL, or whatever, right?
Right.
That's actually called facets.
I was just wondering here how a facet differs from criteria. Like criteria looks like it's, price should be less than 13, and if a facet says publisher should be that, then that's also okay.
No, it's actually a great question. I have a feeling it's like, again, I don't know what was his intent, but I'm just recollecting a typical e-commerce website. There's usually top level filters, and then there's left hand side filter. So this criteria,
Oh,
I don't know, the criteria here, like the title is probably on the search bar itself,
right,
and
right.
then the price and the sorting is on the top level filtering.
Right.
It's like the more foundational things that you would always apply.
It's just there and
Yes,
right there.
right
and
there
then,
at the
and then
top.
you go in the
Yeah,
left
and
tab
then
to
facets
find the
typically
facet.
change by categories, I would say. Like if you're looking at
Right.
sunscreen, you will have like, um,
So price is something that doesn't change by
Correct.
category. Like
Yeah.
everything will have a price, but then if you're looking at sunscreen, yeah, maybe the
Exactly.
category of sunscreen itself would be like a facet.
Yep.
Is a set of results, basically a set of documents. In this case, the documents represent books that I want to return, but they could really be anything. We can think of this as arbitrary JSON blobs that we might want to return. While Elasticsearch does support other use cases, like analytics use cases as part of the ELK stack, I'm not going to talk about this too intensively in this session, just because search is really rich and I want to go into more detail. Now, how does Elasticsearch think about search? Well, there are some key concepts that we have to identify and name before we can go into more detail about that. The first and most important concept is the document. Like I mentioned, documents aren't necessarily PDFs or things like that. They're just JSON blobs, and they can potentially contain anything. The next primitive that we're working with in Elasticsearch is called an index. And index is kind of an overloaded term. In computer science, index is usually referring to how we structure data to make retrieval really fast.
I think that's like standard in MongoDB too, to refer to a JSON blob as a document.
I see. Yeah, it feels like little like document.
It's you would immediately think of. I'm also immediately thinking of PDF documents, or like in this case, he took like a bookstore example too. So it sounds like a document of the book itself. But yeah,
It's like a
just
catalog, I
JSON.
guess. It's a
Yeah.
catalog of books.
Yeah.
Primitive that we're working with in Elasticsearch is called an index. And index is kind of an overloaded term. In computer science, index is usually referring to how we structure data to make retrieval really fast. In this case, an index is just a collection of documents that we want to make searchable. Within an index, we have two relevant concepts. One is called a mapping and one is called a field. The mapping is going to specify, in some sense, the schema that I want to be searchable on my documents. So my documents might have dozens of fields, but my users may not need to search all of those. My mapping, in some sense, is telling the search engine, Elasticsearch, which of those fields are pertinent, and then what are their types. So in this case, I can tell Elasticsearch that the price is always going to be a floating point number, and as a result, Elasticsearch can organize that information so that I can have range queries, and I can find price less than $13. So with our terms in place, we can now talk about how we actually bring docs into Elasticsearch and how we make them searchable. Elasticsearch provides a RESTful API, and it actually has a pretty good one. So if you haven't designed a RESTful API before, it's actually a useful one to look at, both so you can get some ideas about what a solid production level API looks like and how they handle some complicated corner cases. The very first call that we're going to make is this put to / whatever our index name. So this is creating a books index. And I can specify some configuration parameters, but all of them are optional. I'll get into what shards and replicas are a little bit later. Important thing here is this creates me an index. I don't have to specify a mapping, but I can. And the reason that I might want to is because if Elasticsearch can't infer the types of the fields, which ones I want to search, particularly complex configurations, it may make some mistakes. There's also a lot of overhead to having Elasticsearch guess at what your mapping might look like, because it's going to be indexing a bunch of fields that you may not care about. Now note the field types here have a ton of implications. We talked about how the price we wanted to be able to do range search on, so that's available here. Note also that we've got these text and keyword types. Texts allow us to do rich full text search. So if I want to search for great in Great Gatsby, I can do that in a text field. A keyword, on the other hand, is opaque. Each of the tokens is kind of a unit. And so this is really appropriate.
I was wondering about the REST API stuff. Like, shouldn't we like slash indexes slash books. Like books is the name of the index that we're giving it. So like just straight up slash books. Like
Yeah, I think it could have been a much better way of putting the whole API pathway better, I guess.
yeah, maybe he's just showing at the end, and I just saw it and got confused because I thought books was an existing thing into which we're adding an index, but books is the new index that we're adding.
I am also slightly confused. Like, is he showing how to add an item into a book category? I think so. Put
So it's
books.
um he said in the previous slide that there's something called an index, and like his first half of the video was supposed to be how to use Elasticsearch. So this is assuming we already have like a database and like an entire web app, and then now we're adding Elasticsearch to it. So we need to add an index.
Yeah,
So
I think he's trying to
we're
say the books is
putting
all,
an
yeah,
index. Yeah,
books already exists and just you're putting an item into
yeah.
it.
You're you're not even putting an item into it yet. He never explained that part. We're just creating an index of books. I don't know how the items that exist in our database will go to the
I'm just
Elasticsearch.
mapping with what I do at work. Like,
Uh-huh.
so you have seller and consumers, and then this catalog, which is a backend, right? The backend is already designed and is just waiting for the seller to come and set up an item,
Okay.
right? So your backend would be designed with a certain taxonomy that says, hey, L0 is entertainment, and then your L1 is electronics, and then your L2 is, I don't know, like vacuum cleaner or something like that, okay?
Right.
And then some seller comes in, and then as they set up the item, they add in all the details of the vacuum cleaner, and they'll have to choose they basically sometimes choose, and sometimes there's a lot of machine learning involved to, like, the seller can come in and put in whatever item they want, and then we take the burden of ensuring that item is mapped to the right taxonomy.
Oh.
So
Right.
I think he could have actually like given like slightly more application level use case, like for what's, like, it's clear he's going to talk about like selling books and buying
Yeah.
books, right? But yeah, I don't know what this put books is about, but yeah, let's just keep moving on.
Yeah.
Because it's going to be indexing a bunch of fields that you may not care about. Now note the field types here have a ton of implications. We talked about how the price we wanted to be able to do range search on, so that's available here. Note also that we've got these text and keyword types. Text allow us to do rich full text search. So if I want to search for great in Great Gatsby, I can do that in a text field. A keyword, on the other hand, is opaque. Each of the tokens is kind of a unit. And so this is really appropriate for places where, for instance, my set of categories is fixed, maybe in the UI, and the users can click or select from the available categories. This guarantees that I can do those lookups lightning fast, think a hash lookup, but it won't allow me to, for instance, search for all categories that contain the word fiction when that might include nonfiction. Note also here that I am including this nested reviews. This, if you're familiar with normalization and denormalization, might be a little bit clear, but what we'd like to be able to do is answer our search queries with as few requests as possible. And by nesting the reviews in the document, we can basically construct queries where we can say, I want specific types of books that have certain reviews. Now, this is not without its downsides. If reviews are changing a lot, or if my queries rarely touch them, this is actually going to be really expensive for me to maintain that way, and I might actually be better served by creating a separate index for them. But in this case, I'm showing you what this might look like and assuming that reviews aren't going to be shifting a lot, but that customers care about them. Next, let's talk about adding documents to our index. This is dead simple. I make a post request to this _ doc endpoint inside my index, and I pass all of the document's contents. When I do this, Elasticsearch is going to respond with a basically success message that tells me a number of details. For instance, what was this document's identifier, what was the index it was created into, and this version number. The important thing here is that Elasticsearch is a distributed system. We could be making updates from any node, and they might take some time to percolate through the system. So it's really important that we handle collisions and concurrency. This is particularly relevant when we start to talk about updates. For updates, the simplest possible API is to make a put request to this doc endpoint with the ID that I'd seen earlier. I pass in the entire document body and I can update it. Now, this is probably overkill if I just want to change the rating on one of the reviews, for instance, but it also has some downsides in that if two updates are submitted simultaneously, the last one wins. This is where that version identifier comes in. What I can do is in my update, I can pass in the version number, and what Elasticsearch will do is it will reject that update if that version number doesn't match. This gives me a chance to handle the collision or the conflict on the client. My client can then go and query what the latest version is, take a diff, decide what to do, and resubmit its request. This is actually a pretty common pattern.
I'm slightly confused. Like, what does he mean by version? Is he referring to the version of the book or version of something else altogether?
Yeah, I wasn't sure either. I was thinking he'd explain, but like, yeah, I kind of got lost.
I think
Where-
I'm connecting it with some of the things I already know because I worked very closely with my search experience, and there
Yeah, this part, like with the /_doc, that's like adding an item, right? Like that's all I understood. But
that's
like,
right. There's actually lots more. I would say like two things, right? Like when you add a book, there could be other people who come and add a book, and then there are duplicate listings. And so, how do you
Right.
merge those duplicate listings? And then there's this whole concept of if you are posting a book of Harry Potter, I'm posting a book of Harry Potter. We both put two different images. So which image should show up on the merged listing? And we have something called like some sort of ranking internally that will choose the best image. I mean, there's so many aspects about search. I feel it's not covered, but that's okay. But
yeah,
the
we're focusing just on Elasticsearch, right?
correct. But what I don't understand is like what was the version thing that he was talking about?
Me neither. Should we replay? Did he explain something that we missed?
I think once we play again, it'll.
Pattern in distributed systems, and it's just a way to ensure that the update happening is the one that we would anticipate. Another strategy here, which actually doesn't solve the race conditions, but solves part of the problem, is that I can make field-by-field updates by posting to this underscore update endpoint. And in this case, I'm simply bumping the price from $13.99 to $14.99. Okay, so we've talked a lot about how to insert and update documents as if Elasticsearch is a document database, and it kind of is, but the key thing here that we want to get into is search. Well, fortunately, search is really straightforward too. There is this nice API endpoint underscore search, which sits on the index and allows you to search using this query language that's basically JSON and very SQL-like in nature. So if, for instance, we wanted to allow searches by title where it contains a specific word, then we can just simply do a match query with great in the body. If we wanted to extend that by saying that we also want it to be less than $15, we can do that. And then if we wanted to have a query of books where the reviews had this comment excellent and their rating is greater than or equal to 4 out of 5, we can do that too. Now note these are GET endpoints. You can't actually put this in the body of a GET request. It doesn't actually meet standards, or you can actually stuff this into a query parameter, but you're limited by the size of a URL, which I think is 2048. Someone in the comments, please correct me.
Oh my god, I don't know all of that. Like, so this just goes back to the previous videos we watched, right? Like query parameter and what's that? Path parameters.
Yeah, this is not query parameters. This is like when you're querying your database. This is different from that one. So this is, I've seen this before in MongoDB, right? Like this is what it looks like. Like everything is like nested inside, like you see price, and then less than equal to is nested inside that as a key, and then there's the number inside that. Yeah.
It's also possible to post here, although that's a little bit out of canon in that most of the time when you're doing search requests, you're expecting them to get, they're not actually mutating anything. But the important thing here is this API is really nice and convenient and allows you to specify arbitrary search criteria, the first part of the search product that we talked about earlier. Now, once I've got search results, they're going to come back to me in an API that looks like this. Elasticsearch is going to conveniently report to me how long that search took, whether it timed out, how many shards it hit. Again, we're going to talk about this a little later. And then it's going to tell me how many hits, and it's going to return the contents of those documents to me. Now, this is configurable, and in some sense, you may not want to return the entire document in your search results, but Elasticsearch has this underscore source, which is basically that source document that you originally uploaded. It's also possible to return only specific fields from the document. I may only want the ID or the title. I'm always going to get the document ID inside of Elasticsearch. There's also this field called score, which is trying to calculate the relevance of the document to the query that I've input. And that brings us to the second part of our search product, which is the sorting. Just like searching and filtering, Elasticsearch is a pretty extensive API to allow you to specify whatever sort order you want. So in this first instance, I'm sorting exclusively by price, whereas in the second instance, I'm sorting first by price and then by publish date. Remember that I need one field to be the first and most important sort order. The remaining fields are basically tiebreakers. I can also specify scripts. Elasticsearch has a language they call Painless, which allows me to specify basically formulas that I can use to calculate. So this would be the price with a 10% discount. Doesn't make any sense as a sort order, to be frank, because the sort doesn't actually change, but you get the general idea that you can pass in a formula here. I can also sort by those nested objects and fields. So if I wanted to sort by the highest review, I could do that as well. Elasticsearch will allow me to specify the sort order very rigidly. If I want to, I can tell it exactly which fields to order on. Or I can use that underscore score field that we talked about in the results set earlier, which basically orders by relevance. Now, relevance is a really deep topic. There's some machine learning and statistics aspects to this, but some of the simplest algorithms are actually pretty intuitive and easy to understand. So the most simplest of them all is one called TF-IDF, Term Frequency Inverse Document Frequency. And there's two fundamental observations here. First, the most relevant document probably contains my term more frequently. If I'm searching for Elasticsearch, I want it to mention Elasticsearch a lot. The second thing is I'm going to favor those words that don't appear very frequently across all my documents. So as an example, if I'm searching for Elasticsearch Guide, and I've got two documents, one is a short document, which is functionally an Elasticsearch guide, and then the second is a summary of a court case about some weapon being handed to a guide and the prosecutor using the technology. Which one should I prefer? They both contain Elasticsearch and Guide. Well, the first term frequency is going to tell me that Elasticsearch appears very commonly in this document. So it's going to get a score boost just by the number of times that Elasticsearch appears. The next thing we're going to note is that Guide actually appears in a lot of documents. It not only appears in my Elasticsearch Guide, it appears in court cases, it might appear in a birdwatching guide, and as a result, it's a relatively uninformative term. So what TF-IDF is going to do is it's going to score those items which contain the keywords that are densest and don't appear in many other places higher than those keywords that maybe don't appear very often or appear in almost all the rest of the documents in my corpus. The default scoring algorithm is not actually TF-IDF, but it's a close variant, and it's a good enough approximation. You can assume that Elasticsearch is basically making some statistical inferences based on your documents if you don't specify a specific sort order. Now that we've filtered and sorted the results, we're almost ready to send them to the user, but we've got one last step, which is we might have millions of results that we could potentially return, and most people aren't going to scroll to actually see all of them. It'd be madly inefficient. So we need to institute some sort of pagination. There are two types of pagination, stateful and stateless. Stateful pagination requires that the server keep track of something, so that way it knows.
Yeah, so seems like we'll ignore all of the words that occur repetitively. Like if there's and in a search, then and will be everywhere, and we ignore it.
Do is it's going to score those items which contain the keywords that are densest and don't appear in many other places higher than those keywords that maybe don't appear very often or appear in almost all the rest of the documents in my corpus. The default scoring algorithm is not actually TF-IDF, but it's a close variant, and it's a good enough approximation. You can assume that Elasticsearch is basically making some statistical inferences based on your documents if you don't specify a specific sort order. Now that we've filtered and sorted the results, we're almost ready to send them to the user, but we've got one last step, which is we might have millions of results that we could potentially return, and most people aren't going to scroll to actually see all of them. It'd be madly inefficient. So we need to institute some sort of pagination. There are two types of pagination, stateful and stateless. Stateful pagination requires that the server keep track of something, so that way it knows what the next page is. Usually you're talking about cursors here. In stateless pagination, we're going to pass in some sort of parameter that allows us to localize approximately where in a result set we'd like to look. So as an example,
I think it's a very good topic he's talking about. Like if you're searching for squishies or something, right? Or plushies or whatever, and then you're seeing like 100 search results, and then you're going to the second search result, you're actually persisting some aspects of your search before. Like maybe you filtered it to less than $15 or something. So that gets persisted over in all the other pages.
Ah,
Is
right.
is that what he's referring to? I don't know. What does it mean?
Uh,
What stateful and
I mean,
stateless?
I was thinking he was going to talk about cursor-based. Oh, maybe that is what he's referring to. That makes sense. I thought it
example,
was
this-
like cursor-based and the other one.
This from
Which is
and
page
size
number.
query is simply going to take results starting with the index of from, 0, and pages of size 10. It's going to take the first 10 results and return them to me. When I query again for the next page, I'm going to increment that from to 10. I'm going to keep the size the same, and that will give me the next 10 for a total of 20. Very straightforward. I can also use this search after. So in this case, I'm sorting by date and ID. When I get to the bottom of my results, I'm going to have a date after which there are no more results in subsequent pages, and an ID after which there's no more results. What this is telling Elasticsearch is it's saying, don't return me any results that might be before these two quantities. These are both comparable, but search after is preferable, particularly in the cases where you want to go deep into the pagination, because this requires that me get all the results, and then we're going to slice into that result set based on the inputs. Whereas this actually allows me to restrict the documents that I'm querying based on this search after. After I've gone deep into the result set, I may actually have a much smaller corpus of things that I can search over, and so Elasticsearch has to do less work. It's a kind of clever idea. Now, both of those search types have a problem, which is the index is constantly changing. New documents are being added, some are being deleted. In the worst case scenario, you actually have a document which would have been on the next page, but changed, maybe due to a deletion, and bumped up to the page that you were just on. If that's the case, then your pagination, whether you choose search after or the from and size, is going to miss a document. So how do we deal with this? Elasticsearch supports a point in time search. And the idea here is I can create a point in time where Elasticsearch is going to snapshot what the index looks like at that period. This is going to return me an ID, in this case 46T0. And I can use that point in time while I'm searching. Note I need to specify a keep alive. This is actually pretty expensive to maintain, and so I need to signal to the server.
This is cursor-based pagination. I didn't think about, the instance of deletion.
I don't know. What is cursor-based pagination?
Like we have the item ID of the last item that we looked at, and then the next stuff we want is going to be after that item ID. So in this case, insertion isn't going to lead to duplication. Remember we talked about this? Like when you get the next 10 things, when you get the next 10 things and then there are more inserted at the top, then you'll get duplicates of it. But here he's talking about a very interesting case where there's deletion. So like in the first page, something has been deleted. So the first result of the second page will actually be now move to the first page. Yeah, so which will cause an issue on both the things.
I just wish like whatever examples he's showing, and I don't know if it's just me, it just feels like there is some user action that is tied to this, right? Like he
said the index is constantly changing, but he has to say somebody must have inserted something into it and somebody must have deleted something into it. Yeah. He's actually too into like Elasticsearch and uses too many Elasticsearch terms to be useful. Like, yeah.
A point in time search. And the idea here is I can create a point in time where Elasticsearch is going to snapshot what the index looks like at that period. This is going to return me an ID, in this case 46T0. And I can use that point in time while I'm searching. Note I need to specify a keep alive. This is actually pretty expensive to maintain, and so I need to signal to the server that I still want it for 1 more minute every time I search. But what this does is it searches based on that snapshot and will guarantee that each page of results is consistent. When I'm done, I need to delete that point in time or let it expire so that I'm not using excess memory on the server. But this eliminates at least a small class of problems that you might have with respect to pagination. How this point in time is implemented is an interesting point of discussion for the next section of our video. Before we move on, I want to briefly summarize how you can use Elasticsearch in your system design interview. Typically, Elasticsearch is going to be for complex search scenarios. If you need to do geospatial indexes, if you need to do vector search, if you need to do simple full text search like we've described, Elasticsearch is probably your friend. It doesn't necessarily mean that Elasticsearch applies in every scenario, and there are some potential potholes that you need to be aware of. First of all, Elasticsearch is probably not going to be your primary database. While the API that I described looks a lot like a typical document database, Elasticsearch's durability and availability guarantees aren't actually that good, and over time, most people have relied on setting up a primary data source, be it Postgres or DynamoDB, and then using change data capture, CDC, to basically push updates from that database into Elasticsearch.
I think
the idea here is
this one we came across in that Yelp discussion.
Yeah, yeah.
Change data capture.
is Elasticsearch is going to be a little bit behind your database, but it will have all the updates. The next thing is Elasticsearch is going to work best with read-heavy workloads. If you've got a lot of writes happening, or if your writes dominate your reads, you may want to consider whether Elasticsearch is appropriate. There's a lot of ways that you can change the nature of your workload, maybe limit the number of writes or batch them out, but generally speaking, Elasticsearch is going to perform best when we're reading a lot of data. If you're using Elasticsearch, you have to be able to tolerate eventual consistency. It's going to have a delayed version of the data. Eventual consistency is basically endemic to the design of Elasticsearch. If you need strong consistency, if you need to check for double bookings or things along those lines, you're going to need to use a different database. But if you're not using it as your primary database, you already know that. Denormalization is really key to making Elasticsearch functional. If you've got a particular search page, make sure that you flatten all of your data and that you're not trying to make nested relational queries. You basically shouldn't need to do joins in an Elasticsearch search. If you do, you're going to be in trouble. First of all, because joins aren't supported. And secondly, the way that you might bolt on joins by doing lookups outside of Elasticsearch is really going to compromise performance. And the last thing to consider before you use Elasticsearch is whether you actually need it. Elasticsearch clusters are not a trivial matter to operate and maintain. It's a new technology. In a lot of cases, a simple search capability in your existing database might cover your needs. If you need full text search, if you need to index billions of documents, Elasticsearch is your best friend. But if you've got simplistic needs, aim for simple solutions. You don't necessarily need to dig in. So far, we've talked about Elasticsearch.
I feel like there were a couple of keywords that I'll have to double click, like denormalization.
Yeah.
I was just looking up on ChatGPT. It says denormalization in search refers to the process of duplicating or embedding related data into a single document or index to make search queries faster and more efficient, especially in systems like Elasticsearch or Solr. Apparently, in a normalized database like traditional SQL, related data is split across tables to reduce redundancy, but in search engines, doing joins across multiple tables or indexes is slow or unsupported. And then there's some interesting example as well.
Yeah, this makes sense. If you've done like in SQL, there's a bunch of normalizing you do for first order, second order,
Right.
third order normalizing, and then you split the DBs further and further. And here we are denormalizing, so you're like putting everything together so that your search performs better.
Interesting.
Search primarily from the angle of a user or a client. And from an interview perspective, this is still incredibly useful. In a lot of interviews, what you need to be able to do is to point out when you might use Elasticsearch and how it might fit into your overall design. If you're designing Twitter, search might be a peripheral concern for your overall design, and delegating that to Elasticsearch is a completely sensible design choice. In other interviews, either because your interviewer explicitly tells you, don't use Elasticsearch, I'd love to see how you implement some of the core concepts, or because they tell you to implement a system which seems a lot like Elasticsearch, being able to understand what goes on beneath the covers of Elasticsearch is going to be helpful, and that's really what this second section is about. Now, the first thing that you need to understand about Elasticsearch is that it is, in some sense, an orchestration layer for Apache Lucene, which is a low-level search functionality. Elasticsearch handles the distributed systems aspects, the API, how to manage nodes, how to manage backups, how to keep availability and replication, whereas Lucene is trying to make sure that the data is organized and that it's fast. Lucene operates on a single node. Elasticsearch operates at a cluster level. And so as we're peeling back the onion of Elasticsearch, we're going to be progressively talking about the different layers inside of Elasticsearch before we talk about some of the fundamentals of Lucene. The first thing to understand about Elasticsearch as we kind of peel back the layers of the onion is the various nodes that make up a cluster. Now, an Elasticsearch cluster can have a single host or server. Node is not necessarily a physical machine. And a physical machine can take on the responsibilities of multiple nodes. But at a conceptual level, these are the responsibilities that exist inside the Elasticsearch cluster that need to be performed by some hardware somewhere. The first node type is our master node, or a master eligible node. And what happens here is when we spin up our cluster, we are actually specifying seed nodes or seed hosts, which Elasticsearch will try to connect to and then will elect a master of the cluster. We only want one master node so it can make administrative decisions like when we create indexes or which nodes are actually part of the cluster. But the important thing about master eligible nodes is that there is only one master that is elected at any point in time. The next node type is the coordinating node, and you can think of this as kind of the API layer to the cluster. The vast majority of requests that are coming into my Elasticsearch cluster are going to be search requests. And what coordinating nodes are doing are they're taking those requests, parsing them, and then passing them to the relevant nodes that have the data that we need in order to return the search results. Users are, for the most part, interacting with these coordinating nodes. Data nodes are where our indexes are stored. They are functionally where we keep our documents, and they're probably the most fundamental of all the node types. We're going to have a lot of them. Data nodes need to have really heavy I/O, either lots of memory or plenty of fast disk, because the coordinating nodes are going to be sending search requests, and they expect the data nodes to be able to respond. The ingest nodes are like the backend for our service. It's how the documents make their way into the cluster. And finally, the machine learning nodes are not always used, but are for machine learning intensive tasks. And the idea with a machine learning node is these nodes might require access to a GPU and are going to have very different access patterns. Now, each of these node types, by virtue of their responsibilities, actually imply different hardware. My master nodes need to be incredibly robust and reliable. It's very important to me that they're not going down. My coordinating nodes are going to do a lot of network traffic with the outside world. My data nodes, as I mentioned, are actually going to have a lot of disk I/O or need lots of memory. And my ingest nodes are going to do a bunch of analysis of documents. They typically are more CPU bound. And so what this implies is when I set up a cluster, I might actually choose different server or VM types to take on.
I just feel a lot of these things are going just above my head. But as I was looking at all of these 3 round circles on my screen, I started thinking in parallels. Like the coordinating node is the TPM, the machine learning node is the data scientist, the data node is the data analyst, master node, I don't know, whoever that is.
Yeah.
I don't know. I started thinking in some abstraction. I think I want to take a pause on this a little
Yeah.
bit. I feel it's very theory heavy than something that we can work off of, at least little knowledge and connect together. It just feels like a lot of this is like so new to me.
Yeah, same. It's like getting boring, really. Like I'm just like the master notice, and I'm like, I
Dude,
forgot what you said already.
I've been slightly yawning if you didn't notice.
Yeah, I noticed. Yeah.
Actually, I'm thinking, if you don't mind,
Uh-huh.
we can take a pause on this and let's maybe we can review the videos later. I've been tinkering Lovable yesterday.
Okay, let's do that. But like I've been meaning to say this for a long time. We gotta check whether the recording even works. So like